Hey everybody, this is Larry. This is day 6 of the June Leetcode challenge. Let's get right to it. Hit the like button, hit the subscribe button, let me know what you think. And yeah, week 1, day 6. Queue reconstruction by height. Suppose you have a random list of people standing in a queue. Each person is described by a pair of integers hk, where h is the height of the person and k is the number of people in front of this person who have a height greater than or equal to h. Write an algorithm to reconstruct the queue. N is less than 1100. That, you know, just thought that was a little odd. That is not an even number, but that's okay. Okay, so you have only one example, which is this input, and then you have this output. Okay, what is the question asking? All right. So the 7 means this is the height of this person, and 0 means that the number of people in front of this person, all of them are shorter. Okay. So I think the first thing that I want to do is probably sorting. It's just in general, and sometimes you don't need to sort, but sorting is linear plus a little bit more and log n. So in a lot of times it makes it, unless the order matters, and in this case the order of the input does not matter. So giving it a structure helps me think about things in a way that just lets me think about it a little bit better. How do we sort? I think for sorting it makes sense to I was going to say that it makes sense to put the people whom there's no people greater than in the front, meaning that the 7 0, well, no one in front of this person has a higher height, right? So within the same number, or sorry, within the same height, it makes sense to sort the person who is equal to, because it's equal or greater. That means that 7 0 is always going to be in front of 7 1, right? And similarly, 5 0 is going to be in front of 5 2. So I think that makes sense. And then the question is, who deserves to be in front, the shorter person or the taller person, right? Well, by contradiction, it has to be the shorter person, because if that was not true, then 5 0 cannot be 5 0, right? Maybe. Maybe you have to play around. That's assuming that they both have the same k in this case, which you may not get. I don't know if that's necessarily the case, because there's no 5 1, for example. So, where do I go from here? I think there's some sort of forcing function that I have to think about. So within the zeros, it makes sense, but that in theory, if this is 5 1, for example, 5 1 will appear in front of the 7 0, right? So the question is there a way to do this one at a time? And I think another thing that I'm thinking of is, okay, so in these problems, I'm trying to think about an invariant. Let's say that we sorted already. Let's sort this first. People.sort key is equal to, so now we want to sort by, let's just say, the second element and then the first element. Right? And then now let's print that out just for a visualization. So we have this thing, right, which we know it's not correct, but it is. But is there an invariant that we can come up with as we process this from left to right, right? So 5, 0, by definition, this 5, 0 has to be true because it is the 0 and it is the smallest of the 0, right? Because if there is a number bigger than, or sorry, if there's a number small, or yeah, by sort of a contradiction thing, right? Because if there's a number that's bigger than 5, it has to be after it, as we talked about before. And if there's a number smaller than it, that's okay, but then it would not be the first element. So okay, so we can put the zeros in increasing order. And now let's process the 6, 1, right? So 6, 1 is in a good place. So is 7, 1. But then 5, 2 is the curious spot. Because 5, 2 is saying we want to put in kind of like an insertion sort. We want to basically pop off here, and then put the 5, 2 here, right? Between the 7, 0 and the 6, 1, just by inserting in the right place, because in this case we can easily see that the 5, 2, well, it's behind 2 numbers. Is this always guaranteed to be solvable? I guess so. It's not clear from the problem, actually. That's why I was checking, but let's just assume that is, otherwise I don't know. So in this way of insertion, so let's say this is our ongoing thing, we just put 5, 2 after 2 elements, right? And then similarly for 4, 4, we put it before or after 4 elements that are smaller than this number, right? So that's going to be n squared, just essentially like an insertion sort, one element at a time. Let me think for a second whether I can do better. Is there a sort of thing that lets me do, and I'm thinking about like using stacks or queues or something like that to kind of figure out whether, well, or even just comparison sort. So given these 2 numbers, is there an easy way to show which one comes first, right? Yes, not easily. Because if you have that relationship, then you can just do a regular sort, right? Meaning if we could compare this element with this element and figure out which one comes first. And I don't think you can, because 7, 1, for example, could be before the 5, 2 or after the 5, 2. It's not clear by itself, right? And then the question is, well, let's say we're trying to insert the 5, 2. Can we do a sort of a binary search? And then in theory, use like list, that would complicate things a lot. But I don't even know if that's technically the case, because 5, 2 cannot be after 6, 1, and it cannot be before 5 or after 5, 0, right? So, and I would say also, just for clarity, that for competitive programming, this is n is less than 1100. So I would definitely just do the n squared algorithm and then submit and then figure it out later. The other, I feel like I've done this before. So, and I suppose there is binary index tree, maybe something like that, or a Fenwick tree, where then you can do a binary search in that way by binary searching the number of elements that are smaller than 5, or well, in this case it's bigger than 5, but you could do some math. Well, I guess they don't tell you what h is actually, but in theory, well, I mean, that's not a big issue, because you could just reindex order heights from 0 to n, so, and then use a binary index tree. That way, you could, it's possible, but it would be really tricky to do it. So there isn't. So I think there is a very carefully done and log n algorithm where you where you convert each each number into a number from 0 to n, or say n minus 1, I suppose, or 1 to n, whichever you prefer, 0 index or 1 index, and then subtract that from n, or give or take plus 1, so that you could use the binary index tree or the Fenwick tree, or I guess in theory some kind of segment tree, or something that allows you to be like, hey, in log n time, tells you how for a given number how many numbers are smaller than that, or something like that, right? So there's a lot of playing around there. I don't know, like I don't think that that's that's an easy thing to do, but yeah, but okay. I think right now that's all the exploring I'm going to do for this problem. I think for now, let me think. Is there? I think there's a stack-ish, because because it reminds me a bit of the stack thing, and I think there's a way you can merge. Maybe not. Okay. Okay, let's just do the n log. Oh, sorry, the n square algorithm, and then we'll play around. But well, I mean, I think the n square algorithm is straightforward, given what we worked on. But so I'm going to take the hint just to see if I can figure out n log n algorithm just for me learning as well, and maybe you could learn with me. So let's see. What can you say about the position of the shortest person? Okay, we did that. Once you fix the position, okay, I guess that's what we said. Oh wait, no, that's not true. What can we say about the position of the second shortest person? Okay, so let's say we have 5, 0. The second shortest person is here. So that means that, or that means 6, 1. That means that, I don't know. I don't know if that hint helps more than it already does. So maybe we'll look at the discussion forum afterwards together or something. I do want to figure it out, but that's fine. But yeah, so now let's just say answer is equal to this. In Python, there's an insert, right? I forget the exact syntax, but it's okay because it's not common that you want to do this because the insert is O of n. But I think this will be okay. So it's good practice anyway. So now let's do for, what's it, H and K. HK in people. Okay, so now for people already on the queue, let's just go QH, QK in answer. If the person already on the queue, if the height is is so for example, this is 5. We just count the number. Oh, oops, here. Okay, I'm looking at the wrong answer. So for 5, we want to count the numbers that are already on queue that are equal to or greater. Okay, so equal to or greater than k. Let's just go insert I is equal to, let's just do -1 for at the end, maybe. I don't know if that's good syntax actually, but so if this is true, we subtract 1 from k. this should be H. That's why I was a little confused. Okay. And then now if K is equal, do we want it at the exact moment that is equal to 0? Not really, right? Because, so I was thinking like as soon as it hits 0, we put it in, but I don't think that's correct. Because, for example, the 7 would be 0 and then it would be in the front, and you don't want that, right? So, actually, I think that's okay. 0. Let's make this an enumerate. Insert at index, and what are we inserting? Oh, both the HK. So only this, and then we could break. And then if none of these triggers, though it should, this should be an invariant at the end, at the very last element. So let's try that. Okay, well, I guess in the first case, this never triggers, and then it never triggers all the time. So I'm trying to figure out how to do this in a clean way. But okay, let's just do if think of answer is equal to 0, answer that append HK, and then we just continue. Maybe that's a little hacky, but let's just see if it works first. And we can worry about hacky later. Unpack, expect 3, got 2. Yeah, because this is a tuple. Oh yeah, because we convert these to 0, so that's why. Okay, I was just a little bit lazy, so let's just do count is equal to 0, 1, if k is equal to count. Now it seems like it's a little bit incorrect, or because we put 7 and 0. So this should be index plus 1. Okay, so we have a wrong answer. Why is that? So 7, 1. So it should insert. What is our sorted this? There's still going to be an issue. It seems like my invariant is incorrect. That's why you have to be a little bit careful. Because this is our print, so we, after 2 iterations or 3 iterations, have 6, 1, but then 5, 2 gets inserted in front, which is correct. But then the 7, 1, 7, 1, we, so we put the 7, 1 before the 6, 1. So yes, that is something that I have to figure. I think I'm, so our invariant is not true that the first case that we put in. So this is a good start, or this is in the right direction, I believe. But let's think about this. So basically, what we're saying is at the 7, 1, how many numbers are before? So as soon as it saw 7, 0, it thinks it's good, so it inserts right after here, right? Which is not true. What we want to put this is at the bottom, or the last case where this is true. So what we want to do is keep on going until we count as -1 or something, I think, maybe. If count is greater than k, then we want to insert it at, now we want to insert it into index, I suppose. And then else, basically this is so that we insert it at the last place that we can. And then here we just, if we can't, then we just put it in. Time limit exceeded. Didn't really expect this, because this should be at least, or at worst, n square. Unless we keep on, oh, because we don't break. Yeah, okay. So then it just keeps on going. Okay. Yeah, so this looks way better. So once we really understand the conditions, the edge cases of our problem, because sometimes, even though in English you have the right idea, you have to be able to translate it to code. And here we were, or the royal we, I was talking about, oh yeah, you just get the one where, okay, you find the one case where zero, this goes to basically the number of numbers before this that was equal is true, but you have to consider the other case where, well, if you just insert it here, it's going to make a lot of numbers that are smaller than its set. So you have to keep on going. And there is some invariant here in which 6, 1 has to, in this case, because it is 6, 1 is strictly smaller than 7, 1, then that means that the second number will only be lower for this case, so or lower or equal to. So if it's equal to, it has to be later. Okay, let's submit this real quick. I think maybe there's some edge cases around smaller examples, but I'm okay with trying with this. Cool. Yeah, we spent a lot of time on this one. Even though I think I generally had the right idea in the beginning, because I was trying to think of a better solution. So yeah, so this is n squared because for each element in people, we go through O of n people up to O of n people. So O of n times O of n is n squared. The space is O of n because that's, we have to return the answer. So I guess maybe if you're really clever, you could do something in place, but ignoring that for now. Cool. This is a very tricky problem. There's a lot of figuring this out by just kind of, as I say, try to figure out the invariant as it comes through and what it means to go from left to right. And my, I guess it ran away with it. Got rid of the one code status. But yeah, but the idea of, okay, what is always going to be the first element? If it exists, there's always going to be the smallest and with 0 in the beginning. And then kind of construct it one by one in that case, allow us to figure that out. Okay, let's take a quick look at the discussion forum, just because I want to see if there's an n log n or even O of n solution, because I really, it is an important skill to prove lower bound, but in some cases it's very obvious what the lower bound is. For example, if it's linear or if it's constant, it's obvious because there's no because that's like the size of the input or the size of the output. You have to read everything once or something like that, right? But yeah, so let's kind of take a quick look to see, because I don't know if I could find a lower bound for like, oh, can it be done in n log n? Can it be done? Well, it cannot be done in O of n because there's sorting, at least the way we did it. So yeah. Okay, looking at some solution, picking up the torch group people and sort them. Each guy's in there. Okay. I mean, this is also n squared. Yeah, this seems also n squared, but it seems like there are multiple ways of thinking about this problem. So that's so sort and insert. Okay, well, I guess this is the same way we did it, except for that they sort by the tallest person first. So that's actually probably a better way to do it. Because if you sort by the tallest person first, then you can do it in reverse kind of in a way. So you don't have to do this thing where this is a little bit icky when I was writing it, which is that when you have to go to the last person, right? But if you sort it by, like in this case, if you sort 7-1 first, then you could just, when you insert 6-1, you can just put it at the first place where that is true. So that's actually a better way to write this code, and I agree with that. Thanks, Stefan. I don't understand the question. So, is there any other explanation? Okay, wow, there's an n square, so with of n here. Okay, so I'm glad that I don't know. I think there is a way, assuming that there's a lot of code, just because it's either n log n or n log square n, meaning n log n, something like that. Just by using binary index tree, as I talked about, and then binary search, I think. But the complexity is not really worth it, even if you can prove that to be correct. I'm not 100% sure, to be honest, and it seems like no one else did it. But yeah, this is a tricky problem, but I think the n-square algorithm, maybe on an interview, is okay. It's a little bit on the ad hoc constructive side, but that's okay. It really forces you to kind of think about the invariants as you go through it one by one, and the sorting, which is fundamental to a lot of things. Compared to programming, you get these problems all the time where you have to try to figure out what it is, especially on Codeforce. So definitely a good practice into that kind of thing. Yeah, that's all I have with this problem. Let me know what you think. Let me know how you did. This is a tricky one to kind of get right, and also to prove the lower bounds and stuff like that. Yeah, cool. I'll see y'all later. Have a good day. Have a good weekend. And hit the like button, hit the subscribe button. Bye-bye.